We just see that our vector is a solution, we measure the residual. For matrix exponential times vector, there is no notion of the residual. It's not so clear how we check the error. So defining a residual for matrix exponential is a separate research task, in fact. There are papers on that, so only by trial and test at the moment. So what you do, you generate the Euclidean subspace and you use this, and this is a small matrix which is the size of Euclidean subspace, and we only need to compute the function of the small matrix using, for example, Parlet algorithm. The convergence of polynomial approximation may be slow because it is exactly how well, so if you want to bound how good the matrix function is approximated by this, the only thing that you need to, so this formula is exact if our function f is polynomial. If we make k steps, if our function is polynomial of degree k, this is an exact formula, right? So then the obvious bound of this approximation, how well is our function is approximated by polynomial. So it's bounded by the best polynomial approximation. Polynomial approximation can converge quite slowly, even for exponential, for matrix exponential. If you have the large norm of the matrix, it may converge quite slowly. Therefore, the idea which typically works, and we also seen this in the resonance, we need to use something else. We need to use not the Euclidean subspace, but we need to use another type of subspace, which is related to rational approximation. So, if you come, so rational approximation is a classical approximation in the matrix theory. Not numerical, sorry. And even for the functions that are not, so the polynomial approximation, if you have a single point in which your function is not differential, for example, take absolute value of x, then the convergence of the polynomial approximation with the degree becomes 1 over k, where k is the degree of the polynomial. So singularity in derivative at a single point spoils the convergence of the polynomial approximation. For rational, if you have singularity at single points, it typically doesn't matter. So for example, if you have absolute value of x, there is a very good approximation by rational function. And then you can even use what is called Padé approximation, which is a sort of generalization of Taylor series to the rational approximation. So if you approximate exponential function by a ratio of two polynomials, and then you just factorize it, so this evaluation of the matrix exponent reduces to the solution of linear systems with a shifted matrix. So that's what we sacrifice. Instead of matrix by vector products, we need solvers of linear systems, but we get much better approximation. So this is Padé approximate of the matrix exponential in the -1, 5, 1 area, and it's the error of the 10 by 10 approximate. So this is the degree of the denominator. You can take 3, 3, for example. So it's still quite good. And if you take, for example, 0, which is now polynomial, for some reason it doesn't change at all. Why? Okay, so this is my bad. So this is the error of the not of the Padé. This is the error of the Taylor approximate. This is the error of the Taylor approximate for our exponential function. So it's 10 to minus what? 10 to minus 5. Maybe I need to take it better. Yeah, so this is the Taylor approximate in the area of minus 12 to 1. So it does not approximate the original function. If you replace Taylor approximation by the Padé approximate, or for the 3, 3, it's already much better approximation. And if you take 10, 10, so it's 10 to minus 7. And Taylor had 20 terms. So rational function is a much better approximate. Even if you use simple tools like Padé. Computing best rational approximation is actually a very difficult task. There are not too many good algorithms and robust algorithms. So one of the problems of using direct polynomial, again, this is just a sneak peek to this paper of 19 obvious ways of computing matrix exponent. I'm not going to give them describe all 19. There was another paper by some crazy guy in 71, methods of computing matrix exponential. But, okay, scaling and squaring is sort of state of the art, even for Padel. And this uses a very simple identity. So if the norm of A is greater than 1, what you can do, you can just divide it by the power of 2 such that this norm is less than 1, compute this using even Taylor approximation, and then scale. For example, this is what is done in SkyPy. Scaling and squaring for large norm, compute by small Padel approximate, and then go back by matrix square. And this method is good because, well, even the method that utilizes short-Parlet algorithm, if the eigenvalues are close, there might be some problems. This method ignores the eigen decomposition and works directly in the matrix, and the main problem is the normal structure. Okay? So for large scale, we use Krylov or better rational Krylov subspace, so which basically generalizes the idea of rational function to the iterative method. So that's the idea. What is the idea? So what was the idea of using, this is actually a very cool method, proposed maybe 20 years ago. So Krylov subspace is when you take the vector and you generate the product A, B, A squared, B, and so on. Right? This is the Krylov subspace. In this case, you only get matrix polynomials as the base, as the approximate. But if you multiply by the A inverse to the left, you get the rational Krylov subspace. So you simultaneously increase at each step your subspace by 2 vectors. And then you need to write down the recurrence relation, but they are similar. So for the symmetric positive definite case, if the rational R0 reduces to 3-term, and the rational R0 reduces to 5-term, because we need to go to both sides. But still you need to, this is so-called rational R0 method. And you only need to solve linear system with the same matrix. That's very good because you can, for example, factorize it once and reuse this. So you can do it, and the convergence of this method is much better. So you may need maybe 10 here and 10 here. You may need thousands of the basis function for the default file subset. So this type of methods are very difficult to beat for the computation of the matrix function. So basically, this is the same. You generate the basis, and then you compute the function using the same. So one solver, one matrix directed product. One application is so-called graph centrality. So solution for DS is everywhere. Linear DS everywhere, not physics. In graph, you can connect it to graph centrality. So you have the following network, which is so the graph centrality is defined as follows. So the centrality of the node is defined as the element of the adjacency matrix. By the way, what is the meaning of the diagonal element of the square of the matrix? If A is an adjacency matrix, what's the meaning of the diagonal element of the square of the matrix? Yeah, it's degree. It's a number of neighbors. And this one, well, it's a number of second order neighbors. So it's a number of friends, friends of friends, and so on. So this is expressed. Okay, now it's okay. It's a little bit arbitrary, but let's introduce the weighting coefficients, which is 1 over k factorial. Well, it has some combinatorial interpretation. And then you get exactly, this is how we define the graph centrality. You need to compute the diagonal of the matrix function. Actually, computing diagonal of the matrix function is important. Again, there are several applications of when you need to compute the diagonal of the matrix function. You don't need the whole matrix function, you only need the diagonal of the matrix function, or the part of the matrix function. And this is actually much more complicated than computing the matrix function by vector product. So matrix function by vector product is in some sense easy because we can use Krylov method or computing diagonal of the matrix function without computing the full matrix is much more difficult task. But there are methods that try to handle this, but this is not trivial at all. So you're given a large sparse matrix, you need to compute the diagonal of the exponent. Well, I have at least one such problem that no one knows how to solve. You have a large sparse matrix, you have 5 diagonal, and you need to estimate the diagonal for the function that looks like this. So function of h is 1 over 1. It's a so-called Fermi function, and x, h is just Laplacian plus some potential. It's very important for simulating of certain crystals, and we only need the diagonal of f of h. Computing it, very difficult. Without forming the full matrix, the matrices are very large. So you can do it, but also interesting. Let's go further. And just a few words before the end about other types of matrix function. So sine function that I already introduced. This is the projector. And such projector can be useful again if you only need, you don't need to find all the eigenvectors and so on. And these projectors, they may have some starches. They may be, for example, sparse, be sparse. So if you need to compute only part of the spectrum, you can do that. This is also applicable to the solution of certain matrix equations. Yeah, the computation of the sine function is a separate story. Well, you can use this, but there's also it is an example where you can compute the matrix function by using iterations. So if you run this iteration, at each step you take the matrix plus the inverse and you average. And you start from a scaled dimensional matrix, so you can show that this iteration converges quadratically to the sine function. This is, you basically have, so what is the stationary point? The stationary point is, so you need to look what happens at the scalar case. At the scalar case, it happens so you need to find out what are the stationary points, you need to solve the equation. We get this, right? So you get plus minus 1 as stationary points, and then you need to show that everything that is here goes here with quadratic speed, everything that is here goes here with the quadratic speed. This is a very fast convergent iteration. So actually you can show that xk plus 1 minus 1 squared is just xk minus 1 squared. Maybe there's a minus here, but there is also a polynomial version. It's better to use polynomials rather than the inverses. And this is the application of the matrix and function, which I briefly mentioned. Well, this is an example of a matrix equation which is used in stability of the study of stability of the dynamical system. It's called algebraic Riccati equation. So we're already talking about linear equation, but this is an example of quadratic equation. So in scalar case, we can easily solve quadratic equation. Here we have a special form of the quadratic equation with a special quadratic term and linear term. And we need to solve a quadratic matrix equation, which is not an easy task. But for this case, it is equivalent to finding the subspace that corresponds to negative eigenvalues of this matrix. This is a non-trivial observation. And this can be done by the matrix sine function without computing the eigenvalues. You just run this iteration of n. So this is applicable for medium scale dynamical systems with hundreds of degrees of freedom, and it's basically a relay or electric circuits, and it's related to the study of stability of the system. You're given some dynamical system, and then you're trying to find out their properties. That's where this equation is actually used. But to solve this equation, sine function is required. This is what I already mentioned. Square root is used to generate samples. And finally, very few words about matrix equations. Only two things. So if you have, this is called matrix equation, and they're known as a matrix. And there are two important classes of equations. The first is called Sylvester equation, where we have ax plus xb equals c. And if this matrix is the transpose, this is a